this lesson, we're going to talk about where a function is continuous over a certain interval. So we've talked a lot about discontinuities, and now we're going to take a look at how do we know where a function actually is continuous. And a closely related topic is actually the idea of domain. So that's what we're going to focus on for most of the lesson, and it won't be until pretty much the final example where we'll be talking specifically about continuity, and you'll see the connection. So first, let's talk about how do you find the domain. And this, in general, should be review from past years. So we're going to move through it pretty quickly, but we will do it in enough detail that you should be able to pick it up if you don't remember. So, finding the domain. 3 scenarios to watch for when looking for a restriction on your domain. In other words, where your domain is maybe not continuous or your function doesn't exist. And the first is to look out for denominators, because we know that it is a mathematical sin to divide by 0. You cannot divide by 0. So when we have a denominator with an x in it, in order to know what effect this has on our domain, we're going to say that with this expression, the denominator of our expression is not equal to 0. So we're going to write out x plus 1 is not equal to 0, and then that will allow us to solve for x and know what x is not equal to. And remember that if it, in this case we don't actually care, but if it doesn't cancel from top to bottom, we've got a vertical asymptote, and if it does cancel from top to bottom, then what we end up with is a whole. So we move the 1 to the other side, and we end up with x not equal to -1. So that would be a restriction on our domain. This is a value excluded from our domain, or what x is not allowed to equal. In this case, because it's a vertical asymptote. So that's one option. Another option is even root. So this is like a square root, a fourth root, a sixth root, an eighth root, anything even. And the reason for that is because we cannot take square roots of negative numbers. If you try to take a square root of -1, you get an imaginary number, which we are not dealing with right now. We are only dealing with real numbers, so this is a mathematical sin. Will make the universe explode. You cannot take the square root of a negative. We can, however, take the cube root of a negative number. That's no problem. Cube root of -1 is just -1, because -1 cubed is -1. So we can't take square roots, fourth roots, eighth roots, whatever, of any negative number, but we can take a cube root. So when we're looking out for these roots or radicals in an expression, we need to make sure we don't have any even roots of negative numbers. And the way that we actually do that restriction is we say, well, in that case, if I can't take a square root of a negative, I'm going to make this greater than or equal to 0. So the expression under the root, I don't write the root or include the root, but the expression under the root has to be greater than or equal to 0. 0 is allowed. I can take a square root of 0. That's just 0. What I can't do is take square roots of negative numbers, which are numbers less than 0. So again, we're going to take this expression and solve for x. So subtract the 3 and divide by 7, and you get x is greater than or equal to -3/7. So denominators not equal to 0. Even roots greater than or equal to 0, solve for x. And then the last thing that we're looking at is a logarithm. And if you kind of think back to what a logarithm graph looks like, you'll see, remember, it is the inverse of an exponential graph. It kind of looks like this. And we have an asymptote right along my y-axis, or at x equals 0. So when I'm looking at my logarithm, I can see that the domain is everything, all the positive values of x, excluding 0, excluding negative values. So in this case, it's whatever's inside my logarithm is going to be greater than 0. So very similar to a root, but in this case, only greater than 0, not greater than or equal to 0, because I cannot take the log of 0. There's an asymptote there. I never actually get to the value of x equals 0. I've got an asymptote at x equals 0, so I've got to exclude that. So again, solve it for x. I need this to be greater than 0. So I've got x is greater than -1/2. That would be the domain of my function. Okay, so those are the 3 things to watch for. Denominators not equal to 0, even roots greater than or equal to 0, logarithms greater than 0 every time whatever is in that position. Set yourself up an expression and solve. So here we go with some actual examples. So this first one is the first case of a denominator, and I mean my denominator to not equal 0. Now, if there's more than just one expression, one term in the denominator, I may need to factor this, but in this case, all I'm looking at is x not equal to 0, and that actually is going to determine my whole domain. So I want to say I'm going to include everything except x equal to 0. This r with a double bar, that's shorthand for saying all real numbers or everything, and then I'm going to say everything but x is not allowed to equal 0. That would be my domain of this function. Doesn't matter that I actually could factor the top and cancel the x's. Don't care in this case. I'm going to do my domain without any simplification. So this would be my inequality notation when I have just something not equal to. And I also need to know how to write this in interval notation. So you are not required to write this out both ways every time, but I am going to, just so you get used to seeing it, so you get used to the practice, and the answer key also has both methods of writing your answer. So this is inequality notation with a not equals or a greater than equals, those kinds of symbols. Interval notation would be saying I'm going to start from negative infinity, I'm going to go all the way up to 0, round parenthesis means not including 0, and then union together with, again, starting on the other side of 0, round parenthesis to not include 0 up to positive infinity. Round brackets always go with positive and negative infinity because I can never actually equal positive and negative infinity. So this would be another way of writing my answer. This is your interval notation. So again, you need to know how to write them both, recognize them both, but when you're giving an answer, unless it specifies what you need, you can choose which one you want to do. So again, denominator not equal to 0. Looking at number 2, again, I've got a denominator that I want to say, well, that's not allowed to equal 0. And I also have an even root, because remember, if there's no number here, this is a square root, a 2, and 2s are even. So I also need to take into consideration that x plus 5 is greater than or equal to 0. So I have x not equal to 0 from this, and I have x plus 5, just the part underneath. I don't need to include the square root when I'm writing this. X plus 5 greater than or equal to 0. Solve that for x. I get x greater than or equal to negative 5. So if I want to write my answer in inequality notation, because I have this term with the greater than or equal to, I don't need to say all real numbers. I can just say x greater than or equal to negative 5, but also x not equal to 0 from up here, and that would be my answer in inequality notation. If I was going to write the same thing in interval notation, this time I'm not going to start from negative infinity. I'm only going to start from negative 5, and I want it to include negative 5, so I'm going to have a square bracket because of the equals underneath. I'm going to go up to 0. I need to jump over 0, so round bracket on both sides, and a 0. This says I'm jumping over 0, not including 0, and then I'm going all the way to infinity. This would be my other way I could write my answer. So, or either of these is correct. You do not need to write them both. You should be comfortable with writing them both and recognizing them both, but you only need to write one yourself. Next example, taking a look at number 3. I have, again, a denominator, so this whole denominator is not equal to 0, so now I'm actually going to have to solve that for x. So if I want to solve that for x, I'm going to move maybe the root x to the other side, so I get 2 is not equal to root x. Square both sides to get 4 is not equal to x. Should show that, square both sides. So again, if I plug in a 4 here, I should have 2 minus square root of 4, 2 minus 2, and that would give me a problem. That would give me 0, so I know x is not equal to 4. So that takes care of my denominator, and then I also have to take care of my square root. So again, everything under the root is going to be greater than or equal to 0. In this case, there's only an x under the root, so I've got x greater than or equal to 0. And I'm going to put these two together to get my final answer. So x greater than or equal to 0. I'm going to write this first. This is basically saying everything, like writing the r. I need it to tell me what exactly I'm dealing with. So x greater than or equal to 0, and then x not equal to 4. That would again be my inequality notation. Or alternately, again, I'm not going to start at negative infinity because I told I need to be greater than 0. So square bracket to include 0 because of the equal sign, up till 4, jump over 4, so union 4 on both sides, up to positive infinity, infinity always gets a round bracket. That would be my other option. So that is, again, denominators not equal to 0 and even roots greater than 0. But I don't actually write the even root when I write the inequality, just what's underneath it. Example number 4 includes both a logarithm and a fraction denominator. So again, denominator not equal to 0. So this is going to be what's in the denominator. Doesn't matter that it's inside the root, is not equal to 0. If I solve that, I'm going to get x not equal to 4. And I need what's inside my logarithm, so that's the x over x minus 4, to be greater than 0. Remember, with our logarithm, we do not include the equals. We cannot take a log of a negative number. Cannot take the log of 0 because there's an asymptote at x equal to 0. Now, this is a little bit tricky. I can't just outright solve this for x, although it is tempting. I know that I'm going to get a positive number out of a fraction 2 different ways. A positive number divided by a positive number, that would give me something greater than 0. And I could also have a negative number divided by a negative number would also give me something greater than 0. Negative divided by negative is positive. So let's think about what situations would give me positive over positive. Thinking about what would make the denominator positive and what would make the numerator positive. Now the numerator is pretty easy. If x is positive, if I have a positive number that I'm plugging in, I'm automatically going to get a positive number. The bottom is a little trickier because if I plug in anything like 1, 2, or 3, then I see that I'm going to end up with a negative number on the bottom because I have 1 minus 4 is going to give me a negative. So in order to get a positive number, I need a number greater than 4. If I plug in 5 minus 4, that's positive, and if I plug in a 5 on the top, that's also positive. So anything greater than 4 is going to give me a positive over a positive. So this would lead me to the conclusion of x greater than 4. Again, thinking about what would make the top positive, if I plug in a number bigger than 4, top is positive. If I plug in a number bigger than 4, bottom is positive. That's a-okay. Then I'm also thinking about, okay, how could I get a negative over a negative? And again, easy on top because if I plug in a negative number, negative 1, negative 2, negative 3, negative 4, that's fine. And on the bottom, if I'm thinking about the same things, negative 1, yes, that's going to give me a negative. Negative 2, yes, that's going to give me a negative. Remember we said before if I plugged in 1, 2, or 3, that would also give me a negative, but that isn't going to give me a negative on the top. So this case here means I actually need to plug in a negative number, or x less than 0. So I'm dealing with these two cases of x is greater than 4 or x is less than 0. Either of those will give me a positive number inside. If you want to see what's going on, you can actually graph this and see that you're going to have your function at x greater than 4 and x less than 0. So my final answer would be x is less than 0 or x is greater than 4. Actually, I might just join those with a comma. X greater than 4. That would be my domain, those two pieces. Again, that's inequality notation. I can write this in interval notation to say from negative infinity up to 0, not including 0, union from 4 to infinity. That would be my second possibility. All right, so up till now we've been talking about domain, and we can kind of see what's happening here when we've got our domain. If there's ever a break in the domain, there's going to be a discontinuity there. So our function here would be continuous from negative infinity up to 0 and from 4 to infinity. But there's a break, there's a discontinuity where we have these jumps or these breaks. And you could go back and look at the previous questions as well to see wherever we have a break in our domain, we're automatically going to have a discontinuity. But domain is not guarantee that my function is continuous when I come to a piecewise function. The reason for that is with a piecewise function, I could have something like my function coming up from the left, close circle here, and jump coming in off to the right. This would have a domain of all real numbers, but there is a discontinuity. There is a break or a jump in my domain. So I'm not guaranteed to have continuity just because I have a domain of all real numbers. In order to figure that out, I need to check what my y values are on each piece of my function in order to know if there's a jump or not. So first off, I'm just going to look at where I would have natural discontinuities based on the rules of domain that we've been working with. And after that, I'm going to check each of the pieces of my function to see if I do have a jump or not. So looking at my first function, the only denominator I've got here is this 7 on the bottom, but that's not going to give me a discontinuity. So this is continuous everywhere. This one would have the discontinuity at, make the denominator not equal to 0, so x is not equal to 7. And this one would have the discontinuity if I solved it of x not equal to 5. So I'm going to need to keep those in mind, and then I'm going to check each of the pieces. So to see if there's a jump between these two, I need to plug in a value of 0 into both of these. So if I take a look at x equals 0, I say, okay, if I plugged it in up here, this would be 0, this would be 0, and I'd have on the lower part negative 1/7. And if I plugged in x equals 0 to this one, I'd have 3 over negative 7. So this is going to be a discontinuity. It's going to be a jump from negative 1/7 to negative 3/7 when I change between these two pieces. If I look at the value of x equal to 3, if I plug in a value of 3 here, I've got 3 over 3 minus 7 is going to be 3 over negative 4. And if I plug in a value of 3 here, this is going to be 21 minus 15 over 12 minus 20 is 6 over negative 8 is equal to negative 3/4. So at this value, I don't have a discontinuity. It is actually continuous at x equals 3. No problems there. Now let's double check these two that I found earlier. Well, x is not equal to 7 would be a discontinuity if this piece existed at x equals 7. But since this piece only exists from 0 to 3, I can actually ignore this discontinuity because when I plug in 7, I would be looking at this piece, and this piece has no problems with 7. However, this x is not equal to 5. Well, 5 is part of this piece. 5 is greater than 3, so I do need to take into consideration the x is not equal to 5 part of it. So in other words, I've got a discontinuity at x equals 5 and a discontinuity at x equals 0, and everywhere else my function would be continuous. So my function is continuous from negative infinity up till 0. Okay, we're okay with that. But then at 0, I've got this jump, so it's not continuous at 0, but it then is continuous again from 0 all the way up to 5. Remember, we double-checked 3, but it turns out it is continuous at 3, no problem. They're going to link up the pieces. And then, again, from 5 to infinity, we continue to be continuous. So that would be with my interval notation, and with inequality notation, I'm looking at all real numbers where x is not equal to 0 or 5. So if we take a look at the graph, just so you can see the discontinuities, here it is. You can see that there's a jump at x equals 0 and an asymptote at x equals 5. So those are the two places where I have to pick up my pen. Couldn't draw it in all one piece. I would have those little jumps there. So that's it for this lesson. Good luck on your homework and your mastery check.